Hello, everyone. Thanks very much for attending this lecture. I made an announcement today about the schedule for the makeup sessions for tutorials and office hours that TAs are going to have next week. So there are 3 tutorial sections for which we have makeup sessions, and we have makeup sessions for their office hours as well, right? So I made an announcement about that. You know the schedule. Those makeup sessions are optional to participate in for students who are registered in those tutorials, okay? That's the first thing that I wanted to mention. The second thing is that my lecture on Tuesday will be for 2 hours because that is supposed to be a makeup session for June 30th, which was Thursday, right? So that is going to be 2 hours. I will teach from 4 to 6. That will be recorded, and that will be posted on Quarkus. My office hours on Tuesday, in the coming Tuesday, is going to be after that session, okay? So when I'm done with the teaching, I'm available. If you have any questions, you can approach me. And on Thursday also, I will be available. In case you have any questions, I will come to the department, and I will make an announcement about the exact time that I'm available in the department. Your final exams start from August 15, right? So, Thursday is before the final exam. I'm not supposed to do that, but just I think that it might be helpful for you. I will be available next Thursday as well if you have any questions. And I emphasize that please have a look at the previous final exam questions. Try to solve them, and try to solve as many questions as you can because that is going to be helpful for the final exam. In the final exam, we are going to have about 50 multiple choice questions, and it's going to cover the whole thing that I'm going to teach by the end of Tuesday. And you will definitely find it helpful if you solve past exam questions. And if you have any questions, you can approach me during the office hours next week, and I will be more than happy to help you. So today, I'm going to talk about binomial distribution. I will review, there is a remainder of the discussion that we had about binomial distribution that I'm going to talk about. Then I will talk about central limit theorem and how our discussion of binomial distribution might be related to central limit theorem. And after that, I will talk about confidence intervals and hypothesis testing. So the way that the coming chapters in the textbook are organized is like this. We are going to have this chapter about binomial distributions. After that, we are going to have a chapter about central limit theorem. Then there is a discussion about confidence interval for proportions, okay? And after that, hypothesis testing for proportion, okay? So we can have categorical data, and we can have quantitative data, right? When we talk about proportions, like we say, we flip a coin 10 times. How many times it came up head, right? It's a categorical variable. It's either head or tail, right? But we can use a random variable to represent that by a number, and we can have a proportion for that, right? So when we talk about binomial categorical variables, we usually talk about proportions. And in general, when we talk about categorical variables, we talk about proportions. And when we talk about quantitative variables, we talk about mean, right? So when we have a sample from a population, okay, if, for example, we are interested in people's opinion in an election, if someone is supporting the Conservative Party of Canada, for example, or not, that is a discussion about proportion, right? We are interested in the proportion in the population, right? But if we are, for example, discussing the distribution of height for people in Canada, then if you have a sample from the population, we talk about sample mean, for example, and the discussion is going to be about mean, not proportion, right? So in the coming chapters, After we discuss binomial distribution, we will talk about central limit theorem. Then we will talk about confidence interval and hypothesis testing for proportions. And after that, we talk about confidence interval and hypothesis testing for mean, okay? And after that, we will discuss a couple of other tests that they are going to be discussed in the last lecture. So for binomial setting, we had some conditions, right? To have Bernoulli trials, we need to have n number of observations, okay? So the number of observations is fixed, and they need to be independent, and each observation falls into one of just two categories, success or failure, okay? So for every trial, we have success or failure, okay? We flip a coin n times, and every time it's head or tail, right? And if you're considering, for example, 5 times flipping a coin, that is a Bernoulli trial because it satisfies the conditions of the Bernoulli trial, right? Because we need independence, and we need a fixed number of n, and the probability of success in each trial is the same, right? So the coin doesn't remember what happened last time, right? The coin doesn't have a memory. And the probability of success this time, when you flip a coin, is going to be similar to the next time, right? So this random variable, which has Bernoulli distribution, the outcome for that can be 0, 1, 2, 3, 4, 5, right? If you're talking about 5 times flipping a coin, right? So that is something that we discussed before. And this 5 times flipping a coin can be considered just one trial for this Bernoulli, for this random variable which has Bernoulli distribution, right? And I explained that we had the formulation for finding the probability of having a specific number of success when we have a random variable which has Bernoulli distribution, right? We discussed the formulation for finding the probability in that case, and I explained that there are 4 different ways to find the probability. One of them is using the formulation that we have, right? But before that, we usually look at the table, right? Because we have a table for binomial distribution. So if the probability that we are looking for is available in the table, we use the table. And during the last session, we discussed and we solved some examples about how to use the table, right, for binomial distribution. We discussed that. If there is something which is not in the table, then we can use the formulation that we have, right? And if the sample is large, there are 2 situations. One of them that I briefly explained last time is when we have Poisson distribution. So Poisson distribution is an approximation of binomial distribution when we have a large sample and the probability of success for each case, for each observation, is small. So in that case, we are talking, for example, about rare cases in a large population. And in that case, binomial distribution can be approximated using Poisson distribution, right? But that is something that we are not going to discuss in this course, right? We are not going to discuss about Poisson distribution here. But there is another thing which is available to us, and that is when we have a large sample. And when we have a large sample, as I briefly mentioned last time, it is possible to approximate binomial distribution using a normal distribution and use the Z table that we had before to find the probability that we are interested in, okay? So we have a binomial table, but in the binomial table, n, the number of trials that we have, the number of Bernoulli trials that we have can be, for example, up to 20, right? But if you're interested in amounts larger than 20, and if that is difficult, you know, if there's a number which is difficult to find the answer for using your calculator, then you may consider approximating the binomial distribution using a normal model if the conditions that I will discuss about for that are satisfied, okay? So there are conditions that if they are satisfied, you can use normal model as an approximation to the binomial distribution if the sample is large enough, okay? But before I explain that, I want to mention another thing about the concept of independence when we talk about Bernoulli trials, okay? This is also important. So we did some examples, we discussed some examples last time in which I think we selected a sample from a population, right? Or we are going to discuss today, I will see. So, but here is the point. If we are in a room, okay, if we are in a room of 10 people, okay, and we have discussed an example similar to this in the past, when we discussed conditional probability in the past, right? If we are in a room of 10 people, and 4 of them are female, and 6 of them are male, okay? If you randomly select one person, what is the probability that that person is female? It's 40%, right? 4 over 10. That is the probability of choosing one person randomly and finding out that person is female, right? But if you're going to choose the next person, what happens is that if the first person was female, now you have one female less in the room, and the number of individuals in the room is one less, right? We discussed an example similar to this when we discussed the concept of conditional probability. So if the first person was female, and if she is not in the room anymore, what happens is that when you want to select the next person, now what is the probability that this person is female? It's 3 over 9, right? So the probability of this person, this second person, being female is not independent from the first person. Because if the first person was male, this probability would change. If the first person was female, you know, that's different. So the first person being male or female is going to affect the outcome of the second trial, right? So in that case, we don't have independent trials, right? And in that case, we cannot use a binomial model, right? Because the trials are not independent. But imagine that instead of 10 people, we have 1,000 people, okay? Now, 400 people are females, 600 people are males, okay? Now, select one person. The first person that you choose, what is the probability of that person being female? It's 40%, right? But now, when you choose now, she is out of the room, okay? When you choose the second person, the probability of the second person being female, if the first person was female, now the probability is that 399 over 1,000, right? It's still very close to 40%, right? So what happens is that they say that if the sample that you have is less than 10% of the population, okay, you can still assume the assumption of independence is valid. Okay, that is very important. That is why in this course we always discuss situations in which the sample is less than or equal to 10% of the population, because in this course we are always interested in independence, right? The things that we discuss in this course, most of them, when we talk about central limit theorem, when we talk about different concepts related to confidence interval and hypothesis testing, in this course, we are interested in independence, okay? And that is why when we discuss the sample surveys in one of the previous chapters, I emphasize that, you know, in this course, we are going to talk about a sample which is less than or equal to 10% of the population, because we want to make sure that the assumption of independence is valid. Because some of the formulations that I am going to present from now on are not valid if the assumption of independence is not satisfied, okay? So for the binomial, for the Bernoulli trials to be independent, which is, you know, an assumption in Bernoulli trials, we need the sample to be less than or equal to 10% of the population. Okay, that was about independence. Now, I'm going to explain how a binomial distribution can be approximated using a normal model, okay? Now here, you see that we have, in this case, in the figure that we have here, we have 5 trials, okay? And probability of success is 0.5, 50%, okay? This figure is for 50% probability of success, okay? Then we calculate probability of x equals 0, 1, 2, 3, 4, 5, because those are the possible outcomes that we have, okay? So we calculate the probability for each of the outcomes using the formulation that we had for a binomial setting, okay? And we can easily say that because P is 50%, that means that Q is also 50%, right? Because Q is 1 minus P, right? Probability of failure in each trial, right? So here, we are going to have a symmetric figure, right? When we plot the probabilities for different outcomes of x, right? This variable which has Bernoulli distribution. X can be 0, 1, 2, 3, 4, 5, right? Number of success in, for these 5 trials, right? And the probability of having no success is equal to the probability of having no failure, right? Because probability of failure is equal to the probability of success here, right? Probability of having 1 success is equal to the probability of having 4 success, because 4 success is equivalent to 1 failure, right? So in this case, you can easily see that the shape is symmetric, okay? Now, that's one case. Then we go to the next slide, and here we see that when I increase P, when probability of success increases, and imagine that we have 20 samples, okay? Now, if the probability of success in each trial is 90%, okay, every time there is 90% chance for success. So out of 20 trials that you have, you expect that you will have more success, right? Because the expected number of success is going to be n times p, right? It's going to be 20 times 9 is going to be 18. We discussed the expected number of success, or mean, for this random variable which has Bernoulli distribution, right? So as you see here, it's going to be left skewed. It's going to be skewed to the left, because there is, it is less likely to have more failures, right? It is more likely to have more success, because in each trial, success is very likely, right? The probability of success is 90%, right? And similar to this, you can show that if probability of success is very small, like if the probability of success is, for example, 10%, then there's a good chance for failure in each trial, right? In that case, out of 20 trials, you would expect less number of success, and it would be, this figure, this distribution, would be skewed to the right, right? Or right skewed, right? So if P is less than 50%, it's going to be right skewed. If P is more than 50%, it's going to be left skewed, right? For this figure that we have. But what is interesting is that no matter what the value of P is, for example, in the third case, in which P is small, and we expect it to be right skewed, and it's a little bit right skewed. But what we observe is that when we increase the number of samples, when the number of Bernoulli trials increases, it becomes more symmetric, right? So no matter what value P has, if we increase n, it's going to be more symmetric, okay? So in the last case, you see that, for example, for 500 samples, it becomes quite similar to a normal distribution, okay? And P here is 40%, and we would expect this to be a little bit skewed to the right, but because the sample is large, we see that this is symmetric. This is symmetric and unimodal, and it can be proved that this can be approximated using a normal model, okay? And the condition for having a large sample, okay, now the question is how large the sample should be, okay? Is it enough to have like 10 samples, 20 samples, 30 samples, or what? And the condition that we have for that, which is discussed in your book, the proof for this is quite simple. You can have a look at the chapter and see where this is coming from. The condition is that the expected number of success and expected number of failure approximately, just roughly speaking, at least for this course and for the exam that you have, should be larger than 10, okay? NP is mean for the random variable which has Bernoulli distribution. It is the expected number of success. NQ is the expected number of failure, right? So we need to check these two numbers and make sure that they are larger than 10, okay? In that case, if you see an example and you see that the values are not in the table, okay, you're going to see if you can approximate that using a normal model and use the Z table. To make sure that you can approximate that using a normal model, you need to first make sure that the sample is less than 10% of the population. And at the same time, sample should be large enough. How large? NP and NQ need to be larger than 10. An expected number of success and expected number of failure should be larger than 10. This is an approximation. And another condition that will be discussed more in the next chapter is that when you choose a sample, you need to use simple random sampling. Like the way that the sample is chosen from the population, simple random sample, the assumption is that there is randomization, and simple random sample has been used. That we discussed simple random sample in one of the previous chapters. Simple random sample is used for generating the sample. And I will discuss more about this later, but this is what we have. So now how can we approximate this using a normal model? So X is the number of success, right? We have a sample, the sample size is n, and X is the number of success, right? And we showed that under certain conditions, I explained that the distribution for X can be approximated using a normal model, right? Now, what is the mean for this normal model is NP. That is the mean that we had for Bernoulli random variable, right? So we had a random variable, we had n trials, probability of success was P, and the expected value for this normal model is going to be that expected value, okay? So what is the standard deviation? If you remember, the standard deviation for a Bernoulli random variable was this, was the square root of n PQ, right? N is the number of samples, P is probability of success in each trial, Q is the probability of failure in each trial. 1 minus P is Q, right? And you can just use that mu and sigma that we had for Bernoulli random variable in a normal model, okay? Now, you can simply use Z table to find the probability of what you're interested in. And now, if someone talks about proportion, if someone says that instead of probability of, instead of number of success, I'm interested in the proportion, right? Proportion of success in my sample. I have chosen a sample from the population of Canada, and I'm interested in the proportion of people in that sample voting, for example, for the Conservative Party of Canada. Okay, so sometimes you're interested in proportion, not the number of success, right? So proportion, sample proportion, and we use hat just to show that it's a statistic. It's a statistic. It's related to the sample. It's a sample statistic. It's not a population parameter. The proportion of success is x divided by n, right? We count the number of success. We divide that by the number of sample, number of items that we have in our sample, right? So this way, and P, we are interested in P, proportion of success in the population, right? We want to know the proportion in the population. We are interested in P, right? But the formulation that we have here is for the distribution of sample proportion, okay? And I will talk about this more. But for now, just remember, for now, we assume that we know P, we know Q. If we know P and if we know Q, this is going to be the normal model for the proportion in the sample, okay? Now, the number of success, we have a random variable which has Bernoulli distribution, and it depends on the sample that we have. So the first time that you choose a sample, depending on the sample that you have, there is a specific number of success. The next time, there's a specific number of success, and so on. And each time, you can calculate this proportion, okay? You can calculate and find out this sample proportion. Now, this sample proportion is x divided by n. If mean for x is np, mean for sample proportion based on the formulations that we had in the past is going to be that mean divided by n, right? So the mean for sample proportion is the population proportion, right? And this is something which is important. Mean for the sample proportion is the population proportion. And the standard deviation for sample proportion, we know that if we divide the standard deviation, if we divide x by n, the standard deviation is going to be divided by n as well. So this is going to be the formulation, the square root of pq over n. This is going to be the formulation for standard deviation of the sample proportion, okay? So these are the two normal models that we have. One normal model is for the number of success. One normal model is for the proportion, right? Proportion of success. And the proportion of success itself, and in general, every sample statistic itself is a random variable. Proportion of success is a random variable. Why is that a random variable? Because this time, I am choosing a sample from the population of Canada, and I calculate the proportion of success in my sample. I calculate sample proportion. Next time, I have another sample. I calculate sample proportion. Again, I might do this 1,000 times, right? And every time, I might have a different proportion of success in my sample, right? So the sample proportion itself is changing depending on the sample that I have, right? So sample proportion is a random variable itself, and we have found the probability distribution for that. We have found the model for that under certain assumption. It is normally distributed, right? And mean for that is the population proportion, and a standard deviation for that is the square root of pq over n. Now, for now, we assume that we have the population proportion. But later, when we discuss confidence interval and hypothesis testing, we see that in reality, we don't have these population parameters, and we are interested in finding them. And we use the formulations that we have here and central limit theorem that I am going to discuss to figure out where the population parameter is, okay, or approximately is. And another just concept that I want to briefly, very briefly mention, and you can learn more about it if you study yourself, but I just want to mention that because, you know, in the future you might come across that, and just to give you an idea, we have sample statistics and we have population parameter, right? This is what we have discussed many times, right? Every statistic has a distribution because every statistic is a random variable itself, right? Sample mean is a random variable, sample proportion is a random variable. These are all random variables because they depend on the sample that we have, okay? If mean for sample statistic is equal to the population parameter, we say that that is an unbiased estimate of the population parameter. That is a definition of an unbiased estimate. And we have an unbiased estimate when the mean of that estimate, which is a random variable itself, sample proportion is a random variable, right? When the mean of that is equal to the population parameter equivalent to that, like here P, then we say that this estimate that we have, this sample statistic that we have, is an unbiased estimate of the population parameter. And we, you know, we are not going to get into like technical discussions here, but it's usually useful to have unbiased estimates, especially, you know, when it's needed to have some mathematical discussions. It's useful to have unbiased estimates. And if you remember in the past, when we wanted to calculate sample standard deviation, in the formulation for sample standard deviation, we divided that by n-1, right? And at the time, we didn't realize why we divided that by n-1, because it can be proved that if we divide it by n-1, it will be an unbiased estimate of, or an unbiased estimator of the population standard deviation. The mean for that, when you find the distribution of that sample statistic, is going to be equal to the population parameter. This is just something I wanted to briefly touch, you know, the concept of unbiased estimator or unbiased estimator. And if you're interested, you can read more about it. I just thought that it's useful to mention. Okay, so we have a normal model for a number of success. Under certain conditions, the binomial model can be approximated by a normal model. The condition is that the sample is less than 10% of the population. Sample is large enough, meaning that NP and NQ are larger than 10. And we have the assumption of simple random sample. The randomization has been used in simple random sample to choose parameters from, to choose sample from the population, okay? So this is what we have so far, and now we're gonna do some examples, just a couple of examples. According to government data, 21% of American children under the age of 6 live in households with income less than the official poverty level. A study of learning in early childhood chooses a simple random sample of 300 children, okay? Now, obviously, 300 children is less than 10% of the children in the United States, right? What is the mean number of children in the sample who come from households with income less than official poverty level, okay? So the proportion in the population is 21%, right? And because the sample that we have is less than 10% of the population, and simple random sampling has been used for choosing the sample, so we can say that we can use binomial model here, and the mean for the binomial model, the expected value for the binomial model is NP. We have the formulation for that. N is 300, and P is 21%. So the expected value is 63, right? So you have 300 children in your sample, and the question is that how many of them do you expect to be from these low-income households, right? How many of them do you expect? So when we talk about the expectation, we talk about mean, right? The next question says, what is the standard deviation of this number? So a standard deviation, we have the formulation for a standard deviation, right? We are using a binomial model because we have the assumptions for binomial model valid here. And the standard deviation of x is going to be a square root of NPQ. OK, and you can do the calculation, and you're going to see that the standard deviation is this number, which is on this slide. Now, the next question is this. Use the normal approximation to calculate the probability that at least 80 of these children in the sample live in poverty. Be sure to check that you can safely use the approximation. So we are going to check the conditions for using a normal approximation to this binomial distribution, right? And we need to check if NP and NQ are larger than 10. And you can easily check that obviously NP and NQ, when you calculate, they are larger than 10. So we can use a normal approximation for this binomial distribution, OK? Now the question is that what is the probability of x larger than or equal to 80? OK, we have done this before. You find the corresponding z-score. Z-score is x minus mu divided by sigma. And now the z-score equivalent to 80 is 2.41. And in fact, you're interested in the probability of z larger than or equal to that, which is equal to 1 minus probability of z less than or equal to 2.41. And we do this because z table always gives us the proportion on the left-hand side. Z table always gives us a proportion related to z less than or equal to something, right? So we have worked with this many times before, and you know how to do this, right? Then there is another concept that I just want to very briefly mention. You can check that in the book. It's not going to be in the exam. And that is a concept of continuity correction. So we are approximating binomial model using a normal distribution, right? We are approximating a binomial distribution using a normal distribution. And the fact is that when we talk about binomial distribution, we are talking about the discrete random variable, right? The number of success can be 0, 1, 2, 3, 4, and so on, right? But when we talk about the normal model, we are talking about the continuous random variable, right? For example, when we talk about height or weight, it's a continuous value, right? And we can have a normal model for that, right? So we are approximating a binomial model using a normal distribution. But we know that, for example, if we say what is the probability of x is equal to 80, the probability of x equals any specific number for a continuous random variable is going to be 0, right? But for a discrete random variable, it's not going to be 0, right? When we talk about the specific number. So to make a correction about that we don't discuss in this course, and we don't do in this course, if they are looking, for example, for the probability of x larger than or equal to 80, instead of that, we calculate the probability of x larger than or equal to 79.5, for example. And if you are interested in a specific interval, and in the interval, the beginning and the end of the interval is an integer, you just go before or beyond that integer to include the whole interval and to have a correction for the fact that the probability of a continuous random variable being equal to every specific number is going to be 0, right? Probability of x equals 80 is going to be 0, but when x is a continuous random variable, but probability of x equals 80 if x is a binomial random variable is not 0, right? So just to have a better approximation, they may say, okay, find the probability of x larger than or equal to 79.5, right? When you're using the normal model as an approximation for this. This is called continuity correction, and it's not going to be in the exam. It's a very simple concept, which is briefly discussed in the chapter. And if you're interested, you can have a look at your textbook about that. So there are a couple of examples that I want you to solve. They're past final exam questions. And they're at the end of these slides. And I want you to solve them. And if you have any questions, you can approach me during the office hours. You can easily solve these 2 questions. And if you have any questions, you can approach me during the office hours, OK? So let's go for 5 minutes break. And we will start the next chapter at 4. At 4. So please be here at 4 p.m.